In this lecture, we want to study the force exerted on a moving object in a fluid. Suppose it has only translational velocity and the object has no rotation. It's just for simplicity. The relevant quantities should be force, F, which is unknown and we want to obtain it, the velocity of the object, the a characteristic length. At least the object should have a characteristic length. It may have more than one characteristic length. For simple objects such as a sphere or cube, there should be at least one. There is one characteristic length. There are parameters related to the fluid, such as the fluid viscosity, mu, and its density, rho. We want to know with these parameters how many characteristic force can be constructed. Let's see their dimensions. The dimension of V is L T inverse R L, viscosity S. The dimension of viscosity is M L inverse T inverse. This dimension of density is M L to the power minus 3. We are searching for the combinations of monomial power law monomials of these four parameters: V to the power A, mu to the power B, rho to the power C, which has the dimension of force. Now we substitute the dimension of these four parameters. Then we have L T inverse. Then we obtain three equations for these four parameters, A, B, C, and D. The power of M in the both sides of this equation should be the same. Then and T. We have three equations for four unknown parameters. Then there remains one free parameter. Let's say B. Then we have which gives D equal to then the equation is V to the power A 2 minus B, mu to the power B, rho to the power C, R to the power D, which is this combination has the dimension of the same dimension as force. For any value of B, we can take B equal to 0, 1, 2, 1 over half, and any other real value. For example, if we set B equal to 1, we obtain let's call it F1. If we take B equal to 0, we obtain, let's take it F2. For the other values of B, we obtain other quantities which has the dimension of force. For example, let's take B equal to 2. We can take it as F3, and so on and so forth. F1 and F2 is special because in F1, only one parameter of the fluid appears, its viscosity. And in F2, only density appears. But if we take other values for B, we obtain different functions for force. Both of the parameters, viscosity and density, appear in that combination. These two forces, F1 and F2, have different physical interpretation. F1 is due to viscosity of the fluid. When an object moves in a fluid, there is a force which prevent the object to move freely. It's something like friction. It's due to viscosity. In an analytical calculation, it can be shown that the viscous force is proportional to viscosity, characteristic length, and velocity of the particle. The constant which appear here depends on the shape of the object. And the other force, rho r squared v squared, it is due to collision of the fluid particles to the object. Every fluid particle, when collide with the moving particle, there is a momentum transfer between the fluid and the object. There should be a force. This force is proportional to rho, the surface area of the object, which is proportional to r squared, and v to the power 2. Each dimensionless coefficients of F1 and F2 has a dimension of force. The ratio of these two forces, F2 over F1, is trivially it should be dimensionless, and it's a well-known dimensionless quantity in fluid mechanics. It's known as Reynolds number, and it has also a physical meaning. For a large Reynolds number, the fluid is turbulent, and for small Reynolds number, the flow is laminar. When the flow velocity of water emerging from the water tap is low, the water column is transparent and its surface is smooth, like in this image. This case corresponds to low Reynolds number, and the flow is laminar. When the flow velocity is high, it corresponds to a high Reynolds number. The water column is opaque, almost white, and its surface is wavy. The flow is turbulent in this case. We obtain two characteristic force, and we showed that any other choice of B, we can obtain other characteristic forces. In this problem, there are two independent dimensionless quantity, pi 1, which is F over mu RV, pi 2. With any power law monomial of these two dimensionless quantities, we may obtain other dimensionless quantities. For example, Reynolds number. We can choose any of these dimensionless quantities. For example, the equation we are searching for may be this equation, or this equation. Depending on the parameters of the system, each one of these equations may be more useful. In fact, all of them are the same. But for example, for the case of inviscid limit, when viscosity is almost zero, the flow is turbulent. Then in this case, F1, which we have chosen to be mu RV, is irrelevant. F is F2, and it's rho R squared V squared. In inviscid flow and in large Reynolds number. As it is seen here, F depends on the fluid density and the characteristic area, and V squared. In the low Reynolds number, F2 is unimportant and the relevant force is. So in two extreme limits, low Reynolds number and large Reynolds number, the dependence of force exerted on the moving object is proportional to V or V squared. In the medium region, where both of the parameters, viscosity and density of the fluid, are important, the dependence of force on velocity is more complex, and we should use this equation. For example, if the body's shape has more than one characteristic length, for example 2, R1 and R2, then the dimensionless quantities are and the equation governing the moving body in the fluid is something like this, or this. In fact, in this case, in the last case, we have written F over mu R1V in terms of two other dimensionless quantities. For the case of inviscid fluid, turbulent flow, when mu is close to zero, Reynolds number tends to infinity, and viscosity is not a relevant parameter. So, in this equation, the dependence of phi1 over Reynolds number should be in such a manner that the viscosity remove. Then it means that the dependence of phi1 over Reynolds number should be a linear function. Then F is, I have written this as a linear function of its first argument. Then viscosity will be removed, and the force is rho R squared. When some object is falling in the air, for example, a raindrop or a parachute, we should use the parameters of the air. Viscosity of the air is about 2 times 10 to the power minus 5 second. And the density of air is 1 kilogram over. As it is seen, the viscosity is very low. Then for objects, Reynolds number is rho RV over mu. Then it is for a falling object in the air. 1 times RV, 2 times 10 to the power minus 5. So if the object is very, very small, or the velocity is very, very small in such a way that the Reynolds number is a small number, the flow is laminar. Otherwise, for most objects, for example, for a raindrop or parachute, the R for the raindrop is about several millimeters, or a large raindrop it is 1 centimeter, or if the velocity is about several meters per second, for example 1, 2, 3, 1 to 10, then the Reynolds number is about 10 to the power 4, 5, 6, depends on the characteristic length and the velocity. So for most objects falling in the air, we should use F to be rho R squared V squared, and the parameter C depends on the shape of the falling object.